All right, chemistry, this is your video lecture for Chapter 3, Section 1. The title of this section is The Atom, from Philosophical Idea to Scientific Theory. Let's look at the objectives for this section, or this presentation. I want you to be able to state the 3 laws that support the existence of atoms. I want you to be able to list the 5 principles of John Dalton's atomic theory. And I want you to be able to explain the relationship between Dalton's atomic theory and the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. The idea of an atomic theory is more than 2,000 years old. It originates back in ancient Greece with a man named Democritus. He came up with the idea that if you continued to cut a particular piece of matter in half, eventually you would come to a piece that was so small that it could not be cut. Now, in this mind experiment that the philosopher was carrying out, he was assuming that you had some sort of tool that would allow you to cut infinitely small. And his conclusion was it wasn't for a lack of an instrument that you couldn't cut anymore. Is that at a certain point there was a fundamental unit of matter that could not be subdivided at all. And so he called this smallest fundamental particle an atomos. All right, that's Greek. A means not or can't or un, and tomos refers to divisibility or being able to be cut. So an atomos is something that cannot be divided. And so when we say an atom, we're referring to that inability to be split. Now, what we know today is that there actually is a whole level, several levels of particles that are smaller than what we call atoms, but at this time that wasn't known. It was thought to be the smallest thing possible. Now, with Democritus 2,000 years ago, he most certainly did not have the instrumentation to actually cut matter down to the atomic size. It was solely a mind experiment. So this became known as an atomic theory because there was no way to test it. Until recently, scientists have never seen evidence of atoms, until very recently. The law of definite proportions, the law of conservation of mass, and the law of multiple proportions support the current atomic theory. So when we talk about laws that indicate or suggest the existence of atoms, these are those 3. Now, there are several atomic theories. The current model being pushed and studied and taught in schools, or at least the higher levels of science classes, is called the quantum mechanical model. It's actually represented by the diagram on the right. What was thought before the current quantum model is something closer to what we see on the left. Now, this is a traditional view of an atom because, well, it's much more simple to communicate. We have this idea that we have a single large nucleus, and we have these orbits that move around the nucleus, and those are the paths that the electrons take. We know that most people have this idea of an atom in their mind, but realize it's simply one of the atomic theories that have come through history. It's simply one stop on the progression towards a more and more accurate understanding of what an atom truly is. Now, there are several atomic theories. Not all of them are correct in every way, shape, and form. The reason that we're going to cover some of these older ones is because of their historical significance and because we were able to base future study on those theories. So let's look at the law of definite proportions, one of the laws that support the existence of atoms. The law of definite proportions states that a chemical compound always contains the same elements in exactly the same proportions by weight. It's a very definite and exact proportion. That's why we say a definite proportion. Now here we can use weight and mass interchangeably because we're always talking about on Earth in this particular instance, and so the acceleration due to gravity is essentially the same for all matter. The law of definite proportions also states that every molecule of a substance is made of the same number and types of atoms. If you have water, it's H2O. Water is always made at that proportion, 2 to 1. And it is always made of 2 hydrogens to 1 oxygen. Always. That is one of the ideas behind the law of definite proportions.
Table salt, sodium chloride, always consists of 39.34% by mass sodium and 60.66% by mass chlorine, no matter how big the sample is or where it comes from. The salt in the walls of a salt mine might consist of 786.8 tons of sodium and 1,213.2 tons of chlorine, but the proportion is still 39.34% by mass sodium and 60.66% by mass chlorine. A salt shaker with 100 grams of salt would contain 39.34 grams of sodium and 60.66 grams of chlorine. The proportions are still the same. A single grain of salt still contains 39.34% by mass sodium and 60.66% by mass chlorine.
Now, the next law that supports the existence of atoms, the law of conservation of mass, states that mass cannot be created or destroyed, conservation is conserved, in ordinary chemical and physical changes. What you may have heard since then in some other math class is that matter actually can be destroyed. And that's actually true. It can be converted to energy, using Einstein's famous E equals mc squared, but realize that is most certainly not an ordinary chemical change. That is an intense nuclear change that only happens in the core of stars, right? That is not an ordinary condition. So when we're talking about the law of conservation of mass, we're talking about normal chemical and physical processes. So this also means when we start working with equations that the mass of all of the reactants, the things before a reaction occurs, has to exactly equal the mass of all of the products, all of the things that are present after the reaction. So if we look at this in terms of a couple of examples, we have hydrogen combining with oxygen to create water. Notice that when we have these 2 hydrogen atoms combined with 1 oxygen atom, it makes 1 molecule of water. Notice all of the atoms are still present. They've been conserved. They haven't disappeared. They haven't mutated into other atoms or anything like that. Another example is sulfur reacting with oxygen to create sulfur dioxide. All of the atoms that are present in the products were present in the reactants, and all of the atoms present in the reactants are present in the products. Now, this can happen in a number of ways. It can also happen in a degradation or a decomposition reaction. Notice that we have phosphorus pentachloride. That means it has 5 chlorine atoms. After this decomposition occurs, we have phosphorus trichloride. Now that molecule only has 3 chlorines on it. Where did those chlorines go? They can't have disappeared. They must, at the very least, have combined to make their own molecule. We have the exact same number of phosphorus atoms after this reaction, and we have the exact same number of chlorine atoms at the end of this reaction.
This law of conservation of mass states that the total amount of matter in a closed system remains constant. In other words, matter cannot be created or destroyed during ordinary chemical reactions. In chemical reactions, such as the combustion of this match inside a closed container, we find that the mass of the starting materials is the same as the mass of the ending materials. The law of conservation of mass explains why we represent chemical reactions as balanced chemical equations. The number of each atom on each side of the equation is conserved, representing that mass is conserved. The law of conservation of mass works for most things you encounter in daily life. In 1905, however, Albert Einstein showed that matter and energy could be equated with his famous E equals mc squared equation. The implication of this is that the law of conservation of mass will not hold for cases where large amounts of matter were converted to energy, such as in nuclear reactions. The law was revised to become the law of conservation of total mass and energy.
Next law that supports the existence of atoms is the law of multiple proportions. The law of multiple proportions states that when two elements combine to form two or more compounds, the mass of one element that combines with a given mass of the other is in the smallest whole number ratio. Okay, or not smallest, but a ratio of small whole numbers. So let's look at some examples so we can see this in action. They have two molecules here, nitrogen monoxide, nitrogen dioxide. Both molecules are made up of nitrogen and oxygen, so they're the exact same atoms present. Now, with nitrogen monoxide, that's one nitrogen, one oxygen. If we look at the mass due to oxygen, it's 16.00 grams per mole. And if we look at the mass due to nitrogen, it's 14.01 grams per mole. If we create a ratio out of that, we're simply going to divide the 16.00 by the 14.01. When we divide that out, we get a ratio of 1.14 to 1. 1.14 to 1. But now if we look at nitrogen dioxide, it's one nitrogen and two oxygens. So we've doubled the number of oxygen atoms. So that means we're going to double the mass due to oxygen to 32.00 grams. Well, we still only have one atom of nitrogen, so we still only have 14.01 grams of nitrogen. We're going to make a ratio, again, by dividing those two values, so 32.00 divided by 14.01, and we come up with a ratio of 2.28 to 1. Notice how 2.28 is exactly 2 times greater than 1.14. This ratio has increased by a whole number, and they're typically small whole numbers. That is an example of the law of multiple proportions.
The law of multiple proportions states that the mass ratio for one of the elements in a compound that combines with the fixed mass of another element can be expressed in small whole numbers. This law can be demonstrated using two compounds formed from hydrogen and oxygen, water and hydrogen peroxide. A 9-gram sample of water results from the reaction of 1 gram of hydrogen gas with 8 grams of oxygen gas. A 17-gram sample of hydrogen peroxide results from the reaction of 1 gram of hydrogen gas with 16 grams of oxygen gas. We note that the amount of hydrogen in both samples is the same. The ratio of the masses of oxygen in these two compounds is 8 to 16, or 1 to 2. From this, we can deduce that there must be twice as much oxygen in hydrogen peroxide as there is in water, and the same relative amount of hydrogen in both. It does not tell us, however, exactly how many atoms of each element make up the molecule. We now know, for example, that both water and hydrogen contain 2 atoms of hydrogen per molecule, a fact we could not deduce from the law of multiple proportions, which simply told us that we had the same relative amount of hydrogen.
Let's move on to Dalton's atomic theory. Now, moving on from that old version of Democritus, this kind of mind idea, this mind experiment, nothing empirical. But in 1808, John Dalton was able to gather some empirical data, and he was actually able to put together what we would consider a more legitimate natural science idea, his atomic theory. So in 1808, John Dalton developed an atomic theory, an idea of what the atom is, the smallest unit of matter in existence. Dalton believed that only a few kinds of atoms made up all matter. And according to Dalton, elements are composed of only one kind of atom, and compounds are made up of 2 or more kinds of atoms. Now, what he's talking about here is if you look at a chunk of iron, it's made up of iron atoms. And each individual atom is the same. Okay, it's the same. We can combine those elements of iron with atoms of other elements to create different substances. But we're simply combining a small number of atoms to create all matter. So let's move on to those 5 postulates. Number 1, all matter is composed of extremely small particles called atoms, which cannot be subdivided, created, or destroyed. That should be easy to remember. Atoms, atomos, uncuttable, undividable. Number 2, atoms of a given element are are identical in their physical and chemical properties. If they're the same element, they should have the same properties. Atoms of different elements differ in their physical and chemical properties. If they're different elements, they shouldn't be identical in every other way except for their name. That doesn't make sense. Number 4, atoms of different elements combine in simple whole number ratios to form compounds. We already heard about an example looking at water. We have H2O. That is 2 atoms of hydrogen and 1 atom of oxygen. Atoms combine in whole number ratios, as opposed to saying we have 1 atom of hydrogen and half an atom of oxygen. We can't have half of an atom. We can't have 3/4 of an atom. We can't have 0.9 of an atom. None of that. They have to be whole atoms or nothing at all. And then number 5, in chemical reactions, atoms are simply being combined, separated, or rearranged, but they're never created, destroyed, or changed themselves. The actual atoms remain constant. You can only move them around. That's all you can do. Data that's been gathered since Dalton's time, 1808, shows that actually the first 2 principles here are not true in all cases. Now again, we're not talking about this idea, this theory, because it's entirely 100% correct. We're talking about it because it's historically significant. So you will be tested and quizzed on Dalton's atomic theory. But be sure to keep in mind that not all of them are entirely true, and we'll go over that in future sections. Alright guys, that's the end of this video lecture. I will see you next period.